Hi, class. This is our second section from chapter 3, which is covering mathematical models and how to model physical problems. So we talked about compartmental analysis, heating and cooling problems, and population models. And then I'm skipping section 3.3 and deciding to cover 3.4 instead on Newtonian mechanics. And I'm going to be honest right here and say that I'm not a physicist and I don't have a lot of experience doing models, and I'm really more of a theory person. So I hate this chapter, uh, and I hate it. And I hate trying to write out these problems on the board and everything like that. And I don't have a lot of uh, I'm basically just copying my explanation for things from the book and can't give you a lot of deeper insight than what you can read from the book. So my point is that I'm going to talk through some examples, but you're also going to want to read through some of the examples in the book. You'll get a little bit of a better explanation for things. And there are going to be some homework problems that I haven't done examples just like, but there are some similar examples in the book. And so if you can find the similar problem in the book and read through the details, that will help you out. Okay, so how do we model um, a, a problem using Newtonian mechanics? We're looking at Newton's second law of motion, which says that when a body is subject to one or more external forces, the time rate of change of the momentum is equal to the sum of the external forces acting on it. So we're going to write that like dp dt equals uh, the forces, so F is forces, which depends on the time, the position of the body, and the velocity of the body. And P here uh, is the momentum at time t. T, and then this all is Newton's second law. Now the momentum P is the mass of the body times its velocity. And so we can write that like P equals mass times velocity. And so if we sub that in, we get mass is a constant and dv dt equals, we can also write this as mass times acceleration, and this equals our forces. And here this is a of t equals x double prime if t is the acceleration. So what this is here is a second order differential equation, but we have only learned about first order equations now. So we're going to consider a case where we can simplify this. So let's say, suppose our forces doesn't depend on the position, which is kind of a reasonable assumption that where your body is located um, may not matter. You know, whether I don't know you're here or there. It matters that the velocity will matter, but not necessarily your actual position. So we're going to suppose F does not depend on X. Then we have a first order equation, m dv dt equals f of t and v, and this is a first order equation in v. So v is our sort of unknown function that we can find, that we want to try to solve for. So we'll just do one example of this, and that's really going to be it for the video. So here's our problem. We have an object of mass m, which has an initial downward velocity given as v naught, and it's following under the influence of gravity. And so it's telling us now that there are two forces on it, the influence of gravity, gravitational force, and then the force due to the air resistance. We want the object of motion. So let's suppose that we start off at the origin and we have our object here, and we're going to say x of t is the distance the object has fallen at time t, which is to say that x of 0 equals 0. And so what we are trying to solve for, the equation of motion, we want the solution x of t. Okay, that's ultimately what we're after. So we know how to model this based on the velocity and the forces. So our forces, let's do this in red. First we have gravity. So we'll call that F1, which is mg, where g equals 32 meters per second squared. And then our second one is air resistance. And we are told that this is proportional to the velocity, and it's going in the opposite direction. So gravity is going down, but air resistance is going up. So we need it to be in the negative direction. So we'll call this F2 equals negative some proportionality constant times velocity v of t, with b is greater than 0 is the proportionality constant. And so our total force is the sum of all the other forces, so F1 plus F2. Okay, so now we can put this into the equation that we had up here. So let's make some space. And we'll get that mass times dv dt equals F1 plus F2, so that's mass times gravity, minus our B, our air resistance proportionality constant, times V. And we're given that our initial velocity is some V naught. Okay, so this is our equation in V. Once we solve for V, then we'll figure out what X is. Okay, so now the question is, how do we solve this? Well, it's first order equation, and we have a couple tools for solving first order equations. So let's think about what type of equation this is. It is an equation in V. These are all that right there. All of these are constants. And so we can see that we don't have anything crazy going on with our dependent variable V. So this equation is both linear and separable. So we can use either method that we learned in chapter 2 to go ahead and solve it. I'll use the separable method. And so we have m dv over mg minus bv equals dt, and then take our integral of both sides. So this integral down here on the left, we can do a u substitution. I mean, this is pretty simple. I'm just walking through all the details. mg minus bv du equals negative b dv, and then that means that we can replace our dv with negative 1 over b dt. u. So our new integral is going to look like over here. We get all these constants on the outside, negative m over b, and then we have the integral of du, and the whole bottom just gets replaced as u equals the integral dt. So now negative m over b ln of, now I can switch my u back to mg minus bv equals t plus a constant. So if we solve out for t, I wrote out the details, but I'm gonna not explain them. This is what we get, or sorry, we're solving out for v. So uh, this is the velocity equation, and what we really want is our position function x. So now we've got to take the integral of v. So the integral is, again, fairly straightforward because most of those things are constants. And so we can do a u substitution to integrate the e, and we get left with this. So we have this formula, there's a constant in it, so we can solve for that. For c with, we know our initial position, x of 0 equals 0, because we said that we were going to start at the origin. And so once we solve that, we get our final answer. Now, I do recommend that you work out all the details of these by yourself. They're just, algebra and basic calculus. But you're going to have to do these things in the homework problem. So having something where you know the answer to it and working out the details should be helpful to you. It's not necessarily obvious to see without writing anything down how I jump from one step to another, but it should be pretty easy if you write it out yourself. There's some other examples in the book too, in this section that are similar to the homework problem, so you can see how other problems with slightly different parameters can be modeled, and all of those examples will be very, very similar to what's going on in the homework. So that's sort of the end of our discussion of mathematical modeling, and we'll move on to other things next week.